In this module, we will be going over the steps of the transformation protocol, as well as the science behind why we are performing these steps. Let's first review what we mean by transformation. Transformation is when a circular piece of DNA, called a plasmid, enters a bacterial cell. The plasmids that we are using remain exogenous. This means that they do not incorporate into the bacterial genome. They remain separate within the bacteria. Bacterial transformation, at its best, remains a very rare phenomenon. This is because there are a number of barriers working against the entrance of the plasmid into the bacteria itself. Roll your mouse over the red squares to see what some of these barriers to transformation are. The next slide will show you a demonstration of the transformation protocol. The steps of this protocol are performed in order to decrease the effect of the barriers to transformation. Although the effect of the barriers will be lessened, it's important to know that they are still present. This is why transformation remains a very rare event. Okay, so our 10-minute ligation reaction at room temperature has been completed. So hopefully now we have some insert that has been ligated into our plasmid. So now we need to get the plasmid into the E. coli or the bacteria so that then that bacteria can replicate and we can get lots of copies of our plasmid. So in my ice bucket here, these orange tubes are the competent E. coli. So in this case, I'm using E. coli JM101, but you may be using a different strain. All the strains that we have and that are supplied are competent, meaning that they are able to take up exogenous DNA, such as plasmids. The process of making bacteria competent is one of the first ways we start to overcome the barriers to transformation. We make bacteria competent by treatment with calcium chloride. In solution, the calcium ions and the chloride ions dissociate. The positively charged calcium ions help to neutralize the negative charges that are found on the bacterial membrane and the plasmid. You can see in the diagram to the right, the gray circles are the positively charged calcium ions masking the negative charges on the phosphate backbone of the plasmid, as well as the lipids on the plasma membrane. I also have my plasmid in here in the ice bucket. So I'm going to go ahead. So these tubes of competent E. coli already have 2 microliters of E. coli in the tube. So I'm just going to add the transformation components directly to these tubes. One thing that's very, very important to remember is that the E. coli must stay on ice all the time unless they're in a water bath. They come right out of the -80. They don't like to be at room temperature at all. Okay, so they'll... Keeping your bacteria on ice at all times when not in a water bath is another way we overcome the barriers to transformation. The ice cools the bacteria and the solution. As we know from physics, the cooling down of objects slows the movements of the molecules. This helps to stabilize the negative charges on the membrane and the DNA, which makes it easier for the positively charged calcium ions to neutralize those negative charges. They'll be always in this ice bucket. So if you look at your protocol, you can see that, and once again, you may have a different number of tubes. So there's 1 tube for each one of the transformation reactions. So I have 4 in this case. If you look at step 8 in your transformation protocol, we're going to start with adding 10 microliters of each one of our ligation reactions to the corresponding tube that is labeled in the same way. So the tube of E. coli. So I'll just get my pipette out here. So it's set to 10 now. So my insert is going to go into the tube labeled insert, the tube of E. coli labeled insert. So 10 microliters out of here. Done with that tube now. Goes into my tube of E. coli. Close the lid. My tube labeled TE is going to go into the tube of E. coli labeled TE. And finally, the tube labeled water will go into the E. coli labeled water. Now we have one extra tube that I've added. This is the plasmid tube. So this is just getting straight plasmid. It's a lower volume because of course the plasmid isn't diluted with the reagents of our ligation and our restriction digest. So we're only adding 2 microliters of that to our transformation reaction. So I'm going to take my plasmid, which is here, and 2 microliters into the plasmid tube. So now we have our tubes of competent E. coli with the various ligation components in them. What we want to do to mix these is actually just hold them like this and give them a flick. The E. coli don't really like to be vortex. They don't like to be treated too roughly. So we're just going to flick to mix them. It's also a little easier than pipetting up and down. So we can do this quickly. You may also have to check throughout the transformation protocol. Whenever the tubes have been sitting for any period of time, the bacteria may actually settle on the bottom of the tube. And if that's the case, you may have to give them a flick to get them resuspended. So at this point, if we look at the protocol, they're going to sit on ice for 5 minutes. So let's pretend 5 minutes has gone. The next step is actually to incubate these in the 45-degree water bath for 100 seconds.
The 45 °C heat pulse plays another role in overcoming the barriers to transformation. Because this is such a high temperature, much higher than normal physiological temperature, the heat releases lipids from the bacterial membrane. This allows pores to open up in the membrane. These pores fuse with the small adhesion zones to create openings that are large enough for the plasmid to pass through. If we open large holes in the membrane, there is less of a barrier between the intracellular and extracellular environment. This means that things such as plasmids and liquids can flow down a temperature gradient. So recall that it's going to be cooler inside the plasmid than outside because we're briefly putting this tube in the 45°C water bath. So that can help draw the plasmid in. There's also usually an osmotic gradient set up between the intracellular and extracellular space. By opening up larger holes in the membrane, it allows the cell to try and equalize this gradient. So this will also help to draw the plasmid in as water flows into the cell down the osmotic gradient. The incubation at 45°C, or the heat pulse, is an important step in overcoming the barriers to transformation. This heat pulse shuts down the proton pumps. These proton pumps, recall, help maintain the negatively charged intracellular environment. If we shut these pumps down, it increases the amount of positively charged hydrogen ions in the bacteria, and therefore this equals decreasing the net negative charge in the intracellular environment.
So this is actually the 45-degree water bath that we have in the lab. The tubes will just go from here and they will sit in one of these racks in the 45-degree water bath for 100 seconds. Okay, so we'll pretend that our 100 seconds of 45-degree heat shock is done in the 45-degree water bath. We can
consider that there are two phases to transformation. All steps up to this point are considered the competent phase of transformation, which means just getting the plasmid into the bacteria. However, simply getting the plasmid into the bacteria does not mean we have a successful transformation yet. We also need to transcribe and translate and replicate the plasmid. That is the next phase, which is the lag phase.
The tubes came right out of the water bath directly back into our ice, and they sit there for 1 minute just to cool them back down to they're more within the physiological temperature range. The next step now is we're going to add LB broth. So this is basically food for bacteria. They're in the lab. They're normally found in these glass containers. And we're actually going to add 250 microliters of the broth to each one of our tubes.
As we head into the lag phase of transformation, we no longer have to worry about overcoming barriers to transformation because the plasmid is already in the bacteria. However, we want to optimize the functioning of the bacteria so that we can transcribe, translate, and replicate that plasmid. The addition of LB is one of these essential protocol steps to maximize the function of the bacteria. LB, or LB broth, contains nutrients and growth factors for bacteria. This will help to ensure that the bacteria is in its most optimal environment in order to metabolize at its optimal rate.
So again, I'm changing tips in between each one. I'm keeping all tubes and tip boxes closed so that they don't get contaminated. This is particularly important with the LB broth because it's basically food for bacteria. It's very, very easy to contaminate the LB broth if it's left open. Okay, so that's the last one. So once again, we're going to give these just a bit of a flick to mix the contents. So I'm back over here now at the water baths. This time we're going into the 37-degree water bath. It's the exact same as the 45. It's just set to 37 degrees instead, and they stay here. So this is the lag incubation for 15 minutes. So just remember.
Not surprisingly, the lag incubation is a key step during the lag phase of transformation. The lag incubation is the 37-degree incubation for 15 minutes in the water bath. This is important because 37 degrees is the optimal temperature for the bacteria. This time and temperature are required to establish the plasmid in the bacteria. The term establish the plasmid means to transcribe, transrate, and replicate the plasmid. Please make sure you're not confusing this with replicating the bacteria. We are talking specifically about the plasmid. This is incredibly important because transcription and translation of the plasmid mean that the antibiotic resistance cassette on the plasmid will be transcribed and translated. This is essential for the bacteria to survive when we plate it on the antibiotic LB plates. The plasmid must also be replicated so that there are multiple copies of it that are available to be passed to daughter cells when eventually the bacteria divides. We also want multiple copies of our insert DNA, so the more copies of the plasmid in our bacteria, the better.
Remember, the lag incubation is done at 37, but in a water bath. So while our tubes are incubating at 37 degrees for 15 minutes for their lag incubation, we can go ahead and set up part of our cereal dilution that we will need once the tubes come out. So I'm not going to go into a lot of detail on how I do this. You can watch the dilutions video to see that. But I'm going to be doing a cereal dilution. I already have tubes set up here that are labeled -2, -4, and -6, indicating 10 to the -2, 10 to the -4, and 10 to the -6 dilution. The solution that I'm using to dilute the transformation in is 0.5% NaCl. We could use LB, it's a little bit more expensive, so to keep costs down we use NaCl. It's a little friendlier to the cells than water because of the amount of salt in it. So what I'm going to do is I'm going to go ahead and add 990 microliters to each one of these tubes. Now you'll notice that I'm not changing my pipette tip in between this. That is because these are empty tubes and I'm using the same solution in each tube, so there's no need to pipette. You'll also notice how slow I'm releasing the plunger on the pipetter, particularly important with these large pipettes to get an accurate pipette and no air bubbles. So that's that. So these now would sit and wait until our 15-minute lag incubation is done. Now, because this is just a video, we're going to pretend that that lag incubation now is magically done. After the lag incubation, your transformation reactions don't have to stay on ice anymore. They can be at room temperature. So I'm just going to tidy up my tube rack. So here I have the leftover ligation reactions. We don't need those anymore, so they're going to go in the waste. This is the TE that is supplied, so we'll keep that. So the tube that I need to dilute is the tube of cells that's the TE buffer ligation. So we're going to dilute this to 10 to the -6. So to do that, I'm going to put 10 microliters of the cells plus TE into the 10 to the -2 tube. So there's my TE buffer tube of cells, not the stock TE buffer. So 10, actually, I should give these a bit of a flick. They've been sitting for 15 minutes, so the cells are probably settled. You'll get a very inaccurate dilution if the cells are all settled at the bottom and you just take liquid off the top. So make sure you mix that tube. So now we're going into the 10 to the -2 tube. In we go. I'm actually going to give this a quick vortex. I know I said cells don't like to be vortex, but it's just a quick one, and because we're doing a dilution. So I'll do that in between each one. Now we go, take 10 microliters from the 10 to the -2 tube into the -4 tube. Give that a quick vortex. And from the -4 tube into the -6 tube. And that's the dilution. So because the -2 and the -4 tube were only used to achieve our 10 to the -6 tube, we can actually dispose of those to keep our tube rack nice and tidy. So now we're left with 5 tubes. We have our insert, our plasmid only, our H2O, our TE buffer tube that's not being diluted, and our diluted 10 to the -6 tube. Each of these tubes will go on a separate LB or LB plus ampicillin plate. So I will demonstrate that now. So we're going to go ahead now and plate our transformations. I have here, this is an LB only plate. I've already labeled it, and you can see I'm labeling it around the perimeter of the plate, and it is labeled on the agar side of the plate or the bottom. So if we do drop the plates and the lid comes off, we still know what's on the plate, and it's around the outside so that we can easily see the colonies when we want to go to count them. So we're going to begin by lighting our Bunsen burner. So we turn, you can't see it's out of frame, but we'll turn the gas on until we hear it, and then use our flint striker to give it a light. So it seems like not a bad flame right there. So ideally you want to be doing this fairly close to the flame because it gives a bit of an area of sterility. I also have it set up so that I'm going in one direction. I'll be going from the ethanol to the flame to my plate. Okay, cut out there because my ethanol actually had no ethanol in it. So as I said, we go in one direction, from ethanol to flame to plate. We don't ever want to be crossing our spreader over top, our flaming spreader over top of the ethanol. So generally I keep the spreader sitting in the ethanol. Now for the purpose of you seeing, I am going to move the flame out of the way a little bit just so you can see, but ideally you still want to be nice and close. I'm also a little farthest forward than I would like to be. So, to plate this, we need to have our pipetter set at 100, which it is. I'm just going to do one plate. You would repeat this for all of your plates. So, LB only gets the dilution. So we always store the plates with the agar side up because the lids tend to get condensation. So I'll flip it over. Give my tube a bit of a flick to make sure that nothing is settled. Take out 100 microliters. And then all I do is crack the plate open and put just that dollop right in the middle. Now I don't want to waste time because that will start to sink into the agar. I take my spreader, run it through the flame once. I'm now letting the flame burn off. You may be hard to see the flame. And I'm now letting it cool for about 10 seconds. At this point, I'm going to lift that lid. I'm just going to touch the agar to make sure that the spreader's not too hot. And then I start spreading my plate. So I'm going back and forth over the plate from edge to edge while turning the plate at the same time. Notice that the lid is hovering over the plate. That lid always stays over top of the plate. So we go around at least 2 full rotations. I run the spreader through the flame one more time. Make sure it's not on fire. And it goes back in the ethanol. This plate will then, so that I know that I'm done, I would leave it with agar side down until you're done, just to make sure it's all soaked in, and then the plate gets flipped over. So this is our incubator where we incubate the plates overnight. So I just want you to remember that the overnight incubation for the colonies of bacteria to grow on our plate right here is done in this incubator. So it looks like a big fridge. So there's the inside of the incubator, except that it's warm. Plate is going to go there, agar side up, and it stays there overnight. So this overnight incubation at 37 is very, very different than our lag incubation, which is done in the 37-degree water bath for 15 minutes. So just make sure you don't get those mixed up.